Welcome back to Notes of Curiosity, exploring ideas that matter. Hey everyone, Alex and Eve here, ready for another deep dive with all of you.
This time we're looking at a book that's been hugely influential in how we understand the history of science.
Yeah, The Metaphysical Foundations of Modern Physical Science by Edwin Arthur Burtt.
Published way back in 1924.
It explores how philosophical assumptions, often hidden ones, shape the development of modern science.
Especially in physics.
You might be thinking, metaphysics and physics, that sounds intense.
It does. But trust me, Burtt was a surprisingly clear and engaging writer.
And I think this deep dive will help you understand some of those hidden influences behind scientific thought.
Exactly. Burt's work has influenced generations of historians and philosophers of science.
Like who?
Well, think about Thomas Kuhn, the guy who wrote The Structure of Scientific Revolutions.
Oh yeah, sure.
His work was deeply informed by Burt's ideas.
So Burt's impact really rippled outwards.
For sure.
Before we jump into the book, I think it's helpful to know a bit about the author himself.
Absolutely. Burtt was an American philosopher born in 1892, and he passed away in 1989.
Gotcha.
While he wrote extensively on the philosophy of religion, he's best known for this groundbreaking work on the history and philosophy of science.
And he actually spent part of his youth in China before coming back to the U.S. to study at Yale.
Interesting.
He became a prominent voice in the philosophy of religion, which might seem a little unexpected given that his most famous work is about science.
Right, but that's what's so fascinating about Burtt. He's able to connect seemingly disparate fields and show us how they're deeply intertwined.
Yeah.
And get this, scholar H. Flores Cohen has said that Burt's book, though often overlooked, has significantly influenced the history of science itself. Think of it as a shortcut to becoming well-informed on this topic.
Okay, let's set the stage.
Right.
Burtt takes us back to the 17th century.
Okay.
A period of immense intellectual upheaval in Europe. This was a time when the old medieval worldview, based on Aristotelian philosophy and church doctrine, was being challenged by a new way of thinking, a new way of understanding the world.
And this wasn't just about a few new discoveries here and there.
No.
This was a complete paradigm shift, a revolution in thought that would reshape the Western world.
Absolutely.
Burtt highlights this tension between the desire to preserve traditional religious values and the growing power of scientific explanations. As he puts it, there was an intense desire to save as much as possible of the essentials of religious belief.
So we're talking about a clash of worldviews.
We are.
On the one hand, you have this ancient hierarchical view of the cosmos, with the Earth at the center and everything revolving around it. On the other hand, you have this new view emerging. A view that sees the universe as a vast, intricate machine governed by natural laws.
Exactly.
And this clash played out in a very real way with figures like Copernicus and Kepler.
Oh, yeah.
They were challenging not just the established scientific model, the Ptolemaic system, but also deeply held religious beliefs.
Right.
Just think about the resistance Copernicus faced when he proposed that the sun, not the Earth, was at the center of the solar system.
Yeah, what an aha moment.
It's mind-blowing when you consider how radical that idea was at the time.
Absolutely.
Talk about an aha moment. But what drove these early astronomers to challenge the status quo? I mean, why risk everything to overturn centuries of established knowledge?
Well, let's take Kepler, for example. Okay.
He was obsessed with finding mathematical harmony in planetary motion. As Burtt writes, Kepler was possessed by the notion that the universe is built upon an exact mathematical plan.
Okay, so he wasn't just looking for a better model of the solar system.
Right.
He was looking for something deeper, something more fundamental.
Exactly.
Okay.
Kepler believed that God had created the universe according to a mathematical plan. And it was the scientist's duty to uncover that plan.
Okay.
And this shift towards mathematical explanations wasn't just an academic exercise.
No.
It laid the groundwork for modern physics and our understanding of the universe today.
Yeah.
We still rely on mathematical models to describe the universe.
So Kepler's insight, this aha moment, was that math wasn't just a tool for describing the universe.
Yeah.
It was the language of the universe itself.
That's a great way to put it. And speaking of shaking things up,
Yeah.
we can't forget about Galileo.
Oh, yeah, Galileo.
He wasn't just a theorist, he was an experimenter.
His pioneering use of the telescope, his emphasis on observation and experimentation,
Yeah.
those were truly revolutionary.
Here's where it gets really interesting.
Okay.
He famously challenged Aristotelian physics, allegedly by dropping objects from the Leaning Tower of Pisa to demonstrate that objects of different masses fall at the same rate.
Oh, yeah.
Whether or not that story actually happened,
Right.
it perfectly illustrates Galileo's approach.
Exactly.
He challenged established dogma with direct empirical evidence.
Right. Galileo wasn't content to just think about the world.
No.
He wanted to see for himself, measure, test.
Yeah.
And this led him to a really important distinction
Okay.
between primary qualities and secondary qualities,
Okay.
which was crucial for his mechanistic view of nature.
Okay. Explain that a bit more for our listener.
Yeah.
What are these primary and secondary qualities, and why are they important?
Think of it this way. Primary qualities are things like shape, motion, and size.
Okay.
These qualities exist in the object itself, independent of the observer.
But secondary qualities, like color, taste, and smell,
Okay.
are produced in our minds.
Wait, are you saying that color doesn't actually exist in the world?
That's exactly what Galileo is saying.
Wow.
It's a radical idea, right?
It is.
It means that the universe itself is devoid of color, taste, smell.
Yeah.
These are all projections of our minds.
Wow.
This laid the groundwork for a mechanistic view of nature, a view that sees the universe as a giant machine operating according to fixed laws.
Whoa, that's a mind-blowing concept.
It is.
It really makes you question how much of our perception of reality is actually constructed by our minds.
Exactly. And that brings us to another giant of the scientific revolution, René Descartes.
Okay.
Now, Descartes is famous for his emphasis on rationalism, summed up in his famous declaration, cogito ergo sum, I think, therefore I am.
Right. But how did this focus on reason shape his view of science?
Well, Descartes was trying to find an unshakable foundation for knowledge.
Something that could withstand the doubts raised by skepticism? This led him to a dualistic view of mind and matter, which has had a huge impact on Western thought.
Even today.
Even today.
So explain that a bit more for our listeners.
Sure.
Why is this dualism so important?
Descartes argued that there are two fundamentally different realms of existence.
Okay.
The material world, which operates according to mechanical laws, and the mind, the realm of thought and consciousness, which is separate and distinct.
Okay.
As he puts it, there is a great difference between mind and body, inasmuch as body is by nature always divisible, and the mind is entirely indivisible.
Okay, so we've got the universe as a giant clockwork mechanism.
Right.
But our minds are somehow outside of that mechanism.
Yes.
How can something that's not part of the machine control the machine?
That's the million-dollar question, isn't it?
Yeah.
And it's a question that philosophers are still grappling with today.
Right.
But Descartes' dualism had a huge impact on the development of modern science, setting up this idea that the universe is ultimately knowable and predictable, even if our own minds remain a mystery.
I see. So even though Descartes was trying to ground science in absolute certainty,
Right.
he ended up raising even more questions about the nature of knowledge and the relationship between our minds and the world.
Exactly. And that's where Burt's central thesis comes in.
Oh.
He's arguing that figures like Kepler, Galileo, and Descartes weren't just making scientific discoveries.
Sure.
They were operating within a specific metaphysical framework, a set of assumptions about the nature of reality
Okay.
that profoundly influenced their work.
Okay, so it's not just about the scientific findings themselves.
It is not.
It's about the underlying assumptions, the often unspoken beliefs about the nature of reality
Yes.
that shape how we interpret those findings.
Precisely. And those assumptions, those metaphysical foundations, have continued to shape our understanding of the world.
Even today.
Even today. Burtt wants us to think critically about the assumptions we bring to science.
What are the unspoken beliefs about reality that guide our research, our interpretations, our very understanding of what science is and how it works?
So it's like he's urging us to look under the hood, to understand the engine that's driving scientific progress.
Yes.
And often that engine is fueled by philosophical assumptions that we don't even realize are there.
Exactly.
Yeah.
But the 17th century wasn't just about the big names like Kepler, Galileo, and Descartes.
Right.
There were a whole host of other thinkers who were contributing to this evolving scientific landscape.
Okay.
Thinkers like Thomas Hobbes and Robert Boyle.
Hobbes was a bit of a controversial figure, wasn't he?
Yeah.
I mean, he's known for his rather bleak view of human nature, right?
Indeed.
Okay.
Hobbes argued that human beings are fundamentally driven by self-preservation and the pursuit of power. As he famously wrote, the life of man is solitary, poor, nasty, brutish, and short.
Wow.
But what's fascinating is how Hobbes's philosophy was informed by the mechanistic worldview
Okay.
that was emerging at the time.
Yeah. He believed that human behavior, like the movement of the planets,
Okay.
could be explained in terms of matter and motion.
So even something as complex as human behavior
Yes,
could be reduced to the interactions of tiny invisible particles.
that's right.
That's a pretty radical idea.
It is.
Yeah.
And it shows how pervasive the mechanistic worldview was becoming.
Yeah.
And then you have Boyle, who was a pioneer in the field of chemistry.
Mm-hmm.
He's probably best known for Boyle's law, which describes the relationship between the pressure and volume of a gas.
Right. But Boyle wasn't just interested in the practical applications of chemistry.
Yeah.
He was also deeply interested in the philosophical foundations of the field.
Absolutely. Boyle was a staunch advocate for the experimental method,
Okay.
and he rejected the Aristotelian view of matter in favor of a more atomistic approach.
Okay.
He believed that all matter was composed of tiny indivisible particles, which were in constant motion. As he wrote, "I look upon the principles of mechanical philosophy as the most likely to enable us to explicate the phenomena of nature."
So if we zoom out a bit,
Right.
what's the overarching theme here?
The overarching theme is that they were all contributing to a growing trend of explaining the world in terms of matter and motion, further solidifying the mechanistic worldview.
Yeah, okay.
This was a radical departure from the Aristotelian worldview, which had dominated Western thought for centuries,
Yeah.
and it laid the groundwork for the scientific advancements of the 18th and 19th centuries.
Wow.
But it all started with a shift in thinking, a change in the underlying metaphysical assumptions about the nature of reality itself.
That's incredible.
It is. So we've laid the groundwork with these revolutionary thinkers like Kepler, Galileo, and Descartes, but there's another figure we can't ignore when talking about the scientific revolution.
Oh, yeah.
Sir Isaac Newton.
Ah, yes, Newton.
Yeah.
The guy who supposedly figured out gravity because an apple bonked him on the head.
Right.
A classic story, though. I'm not sure if it's actually true.
Right. The apple story might be apocryphal,
Yeah.
but it points to Newton's monumental contribution,
Okay.
the law of universal gravitation.
Mm-hmm.
This law, along with his laws of motion, formed the bedrock of classical physics and our understanding of the universe for centuries.
And this is where Burtt really digs deep, right?
Yes.
He goes beyond just the equations and looks at the philosophical shifts that made Newton's work possible.
Exactly. Burtt highlights Newton's concept of absolute space and absolute time,
Okay.
which he proposed as necessary preconditions for his laws of motion to work.
Okay, hold on. What do absolute space and time even mean?
So Newton believed that space and time existed independently of any objects or events within them.
Okay.
Space was like this vast, unchanging container,
Okay.
and time flowed uniformly regardless of what was happening within that container.
That seems so counterintuitive, doesn't it?
Yeah.
Our everyday experience suggests that time and space are relative. Like, time seems to fly by when you're having fun.
Yeah.
And it crawls when you're bored.
It does.
Yeah.
But for Newton,
Yeah.
absolute space and time were necessary for his mathematical model of the universe to function.
Okay.
And his model worked incredibly well, explaining everything from the tides to the orbits of the planets.
Wow.
As Burtt puts it, Newton developed the concept of absolute motion, as measured against absolute space, into an instrument of marvelous precision and power.
So what's Burt's take on Newton?
Oh.
Is he praising him, criticizing him?
It's a bit of both, actually.
Okay.
Burtt admires Newton's genius,
Yeah.
but also points out the metaphysical baggage that came along with his theories.
Okay.
He argues that Newton's concepts of absolute space and time, while mathematically useful,
Yeah.
lacked empirical justification.
Hmm.
They were postulates, not observations.
Okay, so that raises a big question.
Yeah.
If these foundational concepts in physics are based on assumptions, does that mean the science built upon them is invalid?
That's a great question. And it's one that Burtt grapples with throughout the book.
Okay.
He's not saying that Newtonian physics is wrong,
Okay.
but he's urging us to recognize the philosophical scaffolding that supports it.
Okay.
He's reminding us that even our most cherished scientific theories are built upon a foundation of assumptions
Yeah.
that may need to be revisited as our understanding evolves.
That's a really important point.
Yeah.
We often think of science as this purely objective pursuit of truth.
Right.
But it's clear that philosophical assumptions play a huge role in shaping scientific theories and how we interpret the world.
Absolutely. And that's why Burt's work is so crucial.
Yeah.
He's encouraging us to think critically about science, to question its assumptions,
Yeah.
and to recognize that it's an ongoing process of inquiry, not a collection of fixed and immutable truths.
So we've journeyed through the 17th century. We've seen these monumental shifts in thinking, the rise of figures like Kepler, Galileo, Descartes, Newton.
Yeah.
What's Burt's final takeaway? What does he leave us with?
Burt's central message is this. We need to be aware of the philosophical assumptions that shape our scientific worldview. He encourages us to scrutinize those assumptions, to question them, to recognize that they are not immutable truths, but rather products of a particular historical and cultural context. As he writes in his conclusion, the history of science is an illuminating commentary on the limitations of human reason.
But how does this relate to us? To people living in the 21st century.
Right.
Are you saying that these 17th century debates are still relevant today?
Absolutely. In fact, I'd say they're more relevant than ever. We live in a world saturated with scientific information.
We do.
And it's easy to accept scientific pronouncements as gospel truth.
Yeah, it is.
But Burtt reminds us that science is an ongoing process of inquiry.
Right.
And that the assumptions of one era can become the limitations of the next.
So it's like he's urging us to cultivate a healthy skepticism.
Yes.
Not just accept scientific dogma, but to understand the philosophical underpinnings of what we believe to be true about the world.
Exactly. And to recognize that those underpinnings can, and often do, shift over time.
Yeah.
What we believe to be scientific truth is always provisional, subject to revision in light of new evidence and new ways of thinking.
That's a powerful point.
Yeah.
It reminds me of what Burtt says about how the very concept of space has evolved over time.
Yes. Burtt points out that for the ancient Greeks, space was this hierarchical structure with the earth at the center and the heavens above. But with the rise of modern science, space became this vast homogeneous expanse, devoid of any inherent structure or hierarchy.
So our understanding of something as fundamental as space is shaped by our cultural and intellectual context.
It is.
That's pretty mind-blowing.
It is. And it underscores Burt's point that we need to be aware of the philosophical assumptions that shape our understanding of the world. These assumptions are often invisible to us, but they have a profound impact on how we interpret scientific findings and how we make sense of our place in the universe.
So we've talked about how our understanding of space evolved.
Right.
What about time?
Yes.
Did that concept also undergo a transformation during the scientific revolution?
Absolutely. Similar to space, the concept of time also underwent a radical shift. For the ancient Greeks, time was cyclical, mirroring the natural rhythms of the cosmos. But with the rise of the mechanistic worldview, time came to be seen as linear, uniform, and independent of any physical processes.
So we went from a view of time as something organic and cyclical to a view of time as a kind of abstract mathematical construct.
That's right.
Wow.
And the shift in thinking, like the shift in the understanding of space, had profound philosophical implications. It reinforced the idea of a universe governed by immutable laws, a universe that was predictable and ultimately knowable.
So Burtt is saying that these shifts in our understanding of space and time weren't just scientific discoveries. They were also philosophical shifts.
They were.
Driven by a new set of assumptions about the nature of reality.
Exactly. And these assumptions, in turn, shaped the development of modern physics. For example, Newton's laws of motion rely on the concept of absolute time, which flows uniformly and is unaffected by the events that occur within it.
So we've talked about space and time. What about causality? How did that concept change during this period?
The concept of causality also underwent a significant transformation in the Aristotelian worldview. Causality was understood in terms of final causes. Things happen because they were striving towards a goal or purpose. For example, a stone falls to the ground because its natural goal is to be at rest in its proper place.
So in the Aristotelian worldview, everything in the universe has a purpose, a reason for being.
Exactly. But with the rise of the mechanistic worldview, final causes were replaced by efficient causes. Things no longer moved towards a goal. Instead, they moved because they were acted upon by external forces.
So it's a shift from a teleological view of the universe where everything has a purpose to a mechanistic view where everything is determined by the laws of physics.
Precisely. And this shift had a profound impact on how scientists understood the natural world.
Okay.
Instead of asking why things happen,
Yeah.
they started asking how things happen.
So instead of looking for the purpose of a falling stone,
Right.
they started looking for the forces acting upon it and the laws that govern its motion.
Exactly. And this shift in focus from why to how
Yeah.
was a key factor in the development of modern science.
Okay.
It allowed scientists to move beyond philosophical speculation and to focus on developing testable empirical explanations of the natural world.
Okay, so we've talked about how concepts like space-time and causality changed during the scientific revolution.
We have.
What about the broader philosophical framework within which these shifts took place?
Okay.
What were some of the key philosophical movements that shaped the scientific revolution?
One of the most important philosophical movements of this period was the rise of rationalism,
Okay.
as exemplified by the work of René Descartes. Descartes argued that reason, not experience, was the ultimate source of knowledge.
Okay.
He believed that we could arrive at fundamental truths about the world
Yeah.
through the use of logic and deduction.
So Descartes is saying that we can essentially think our way to knowledge.
Precisely. And this emphasis on reason had a profound impact on the development of science.
Okay.
It encouraged scientists to look for mathematical patterns in nature, to formulate theories based on logical principles,
Yeah.
and to test those theories through carefully designed experiments.
So rationalism provided a kind of intellectual framework for the scientific method.
Exactly. And it also contributed to a growing sense of confidence in the power of human reason to understand the world. This confidence was further bolstered by the successes of Newtonian physics,
Okay.
which seemed to demonstrate the power of human reason to unlock the secrets of the universe.
All right, so rationalism was one important philosophical movement.
It was.
What about empiricism? How did that influence the scientific revolution?
Empiricism, in contrast to rationalism,
Okay.
emphasized the importance of observation and experience as the source of knowledge.
Okay.
Thinkers like Francis Bacon argued that we shouldn't rely on abstract reasoning or ancient authority.
Okay.
Instead, we should observe the world carefully, gather data, and draw conclusions based on that data.
So empiricism is really about grounding knowledge in sensory experience.
Precisely. And this emphasis on observation and experimentation played a crucial role in the development of modern science.
Okay.
It led to the development of new instruments, like the telescope and the microscope, which allowed scientists to observe the world in greater detail than ever before.
Wow.
It also led to the development of new experimental techniques, which allowed scientists to test their theories in a more rigorous and systematic way.
So you've got rationalism, which emphasizes reason,
Yes.
and you've got empiricism, which emphasizes experience. Were these two movements always in opposition?
Not necessarily.
Yeah.
In fact, many thinkers of the scientific revolution saw rationalism and empiricism as complementary.
Okay.
They believed that we need both reason and experience to understand the world. Reason helps us to formulate theories, while experience helps us to test those theories and refine them.
So it's like a kind of intellectual feedback loop.
Yes.
Reason and experience work together to advance our understanding.
Exactly. And this interplay between reason and experience is still at the heart of the scientific method today.
Okay, so we've talked about rationalism and empiricism.
Yes.
What about mechanism?
Okay.
How did that philosophical movement shape the scientific revolution?
Mechanism was the view that the universe is a giant machine
Okay.
governed by immutable laws of nature. This view was popularized by thinkers like Thomas Hobbes,
Okay.
who argued that all phenomena, including human thought and behavior,
Yeah.
could be explained in terms of matter and motion.
So the universe is basically a giant clockwork mechanism ticking along according to predictable laws.
That's right. And this view had a profound impact on the development of science. It encouraged scientists to look for the underlying mechanisms that governed natural phenomena, to break down complex systems into their simpler components,
Yeah.
and to explain the behavior of those components in terms of physical laws.
So mechanism provided a kind of blueprint for scientific inquiry.
Yes.
It told scientists what to look for and how to explain it.
Exactly. And this approach proved to be incredibly successful,
Yeah.
leading to major advances in fields like physics, astronomy, and chemistry. But it also had its limitations.
Okay.
The mechanistic worldview, with its emphasis on reducing everything to matter and motion, struggled to account for things like consciousness, free will, and the purpose of human existence.
So even though mechanism was incredibly successful in explaining the physical world,
Yes,
it left some pretty big questions unanswered.
it did. And those unanswered questions would eventually lead to new philosophical movements,
Yes.
like Romanticism and Idealism,
Mhm.
which challenged the dominance of the mechanistic worldview.
Right.
But that's a story for another deep dive.
Okay, so we've covered rationalism, empiricism, and mechanism.
Mm-hmm.
Were there any other philosophical movements that had a significant impact on the scientific revolution?
Yes, the rise of skepticism also played an important role.
Okay.
Skepticism, as the name suggests,
Yeah.
is a philosophy that emphasizes doubt.
Okay.
Skeptics question the authority of tradition and dogma,
Mm-hmm.
urging people to think for themselves
Yeah.
and to demand evidence for their beliefs.
So it's kind of intellectual independence, a willingness to challenge received wisdom.
Precisely. And this skeptical attitude was essential for the development of science.
Oh.
It encouraged scientists to question established theories,
Yeah.
to design experiments to test those theories,
Mm-hmm.
and to be willing to revise their beliefs in light of new evidence.
So skepticism provided a kind of counterbalance to the tendency toward dogmatism that can sometimes stifle intellectual progress.
It did.
It kept scientists honest, forcing them to constantly test their ideas against the evidence.
Exactly. And it also fostered a spirit of open inquiry,
Oh.
a willingness to consider new ideas and to embrace uncertainty.
Mm-hmm.
This spirit of open inquiry was crucial for the scientific revolution,
Yeah.
which was all about challenging old ideas and developing new ways of understanding the world.
Okay, so we've got rationalism, empiricism, mechanism, and skepticism.
We do.
These philosophical movements, along with the changing concepts of space, time, and causality, really laid the groundwork for the scientific revolution. They provided the intellectual tools and the philosophical framework that allowed scientists to make the groundbreaking discoveries that would reshape our understanding of the world.
They did indeed. And it's important to remember that these philosophical shifts were taking place against a backdrop of immense social and political upheaval.
Oh, wow.
The 17th century was a time of war, revolution, and religious conflict.
Yeah.
These events undoubtedly influenced the way people thought about the world and the role of knowledge within it.
So the scientific revolution wasn't just an intellectual revolution.
Right.
It was also a product of its time,
Yes,
shaped by the social and political forces that were reshaping Europe.
precisely. And this reminds us that science is not some abstract, disembodied enterprise.
Right.
It's a human activity conducted by real people living in real historical circumstances. And those circumstances inevitably influence the questions scientists ask,
Yeah.
the methods they use, and the interpretations they arrive at.
Right. So it's not enough to just focus on the scientific discoveries themselves.
Yeah, it's not.
We also need to understand the historical and social context in which those discoveries were made.
Exactly. Science doesn't happen in a vacuum.
Right.
It's always embedded in a particular social and cultural context. And that context shapes the direction of scientific inquiry,
Yeah.
the interpretation of scientific findings, and the way those findings are used and understood by society.
So we need to be aware of these broader social and cultural forces if we want to fully understand the history of science and its impact on the world.
Absolutely. And that's one of the things that makes Burt's book so valuable.
Yeah.
He doesn't just present a dry account of the scientific discoveries of the 17th century. He places those discoveries within their historical and philosophical context, helping us to see how they emerged from and contributed to a profound transformation in Western thought.
So we've been talking about how philosophical assumptions shaped the scientific revolution and even influenced figures like Newton and Boyle. But Burtt also explores how specific scientific discoveries in this era reshaped philosophical thought. What were some of those pivotal discoveries that shook things up in the world of philosophy?
Well, one of the most significant breakthroughs was the development of a new theory of motion. Remember how we talked about the Aristotelian view of motion, where everything strives towards its natural place?
Right, the idea that a stone falls because it's trying to get back to the center of the universe that seems so strange to us now. But it was the dominant view for centuries. What changed that?
It was a combination of things, really. Copernicus's heliocentric model challenged the idea of the Earth as the center of the universe, and then Galileo came along with his experiments on motion. He showed through careful observation and measurement that objects of different masses fall at the same rate, contradicting the Aristotelian view that heavier objects fall faster.
So Galileo used experiments to directly challenge traditional philosophical assumptions about the world. Is a pretty big deal.
It was a huge deal.
Okay.
It showed that empirical evidence could be used to test and refine philosophical theories. And then Newton came along and synthesized all of these ideas into his laws of motion, which provided a precise mathematical framework for understanding how objects move.
So the development of a new theory of motion was not just a scientific breakthrough, it was also a philosophical revolution. It changed the way people thought about the nature of reality itself.
Exactly. And this new understanding of motion had profound implications for other areas of philosophy, like metaphysics and epistemology, for example. If motion is purely mechanical, as Newton's laws suggest, then what does that mean for concepts like free will and determinism?
Right, if everything in the universe is governed by predictable laws of motion, then does that mean our own actions are predetermined? Are we really in control of our own destinies?
Those are big questions, and they're still being debated today, but the point is that the scientific revolution forced philosophers to confront these questions in new and challenging ways.
So the relationship between science and philosophy was a two-way street. Science was influencing philosophy just as much as philosophy was influencing science.
Absolutely. And that's one of the things that makes the 17th century such a fascinating period to study. It was a time of tremendous intellectual ferment when the boundaries between different disciplines were fluid and when new ideas were constantly emerging and colliding with each other.
It sounds like the 17th century was a really exciting time to be an intellectual. But let's bring it back to Burtt's book.
Wow.
What are some of the key takeaways that he wants readers to walk away with?
One of Burt's central arguments is that the scientific revolution was not just about new discoveries. It was about a fundamental shift in the way people thought about the world. This shift was driven in part by a new set of metaphysical assumptions about the nature of reality.
And those assumptions, as we've discussed, had a profound impact on the direction of scientific inquiry and the interpretation of scientific findings.
Exactly. Burtt argues that we need to be aware of these assumptions, these hidden philosophical frameworks, if we want to fully understand science. And he provides a detailed analysis of how these assumptions shaped the work of key figures like Kepler, Galileo, Descartes, and Newton.
So Burt's book is not just a history of science, it's also a philosophy of science. He's not just telling us what happened during the scientific revolution. He's also trying to help us understand how science works, how it's shaped by our assumptions about the world, and how those assumptions can change over time.
Exactly. And that's one of the things that makes Burt's book so valuable. Even today, it helps us to see science not as a collection of fixed and immutable truths, but as an ongoing process of inquiry, a process that's always shaped by our evolving understanding of the world.
That's a powerful point. It reminds us that science is not some abstract, objective enterprise that exists outside of human history and culture. It's a product of those things, and it's constantly evolving in response to them.
Precisely. And that means that we need to be constantly questioning our assumptions, testing our theories, and revising our understanding of the world in light of new evidence.
So Burt's book is not just a history lesson. It's also a call to action. It's a call for us to be more critical thinkers, more informed citizens, and more responsible stewards of the scientific enterprise.
I completely agree. The Metaphysical Foundations of Modern Physical Science is not just a book for scientists or philosophers. It's a book for anyone who wants to understand the intellectual foundations of the modern world, the assumptions that shape our thinking, and the challenges we face as we try to make sense of a complex and ever-changing universe.
Well said.
It's definitely a challenging read.
It is.
But I think it's a rewarding one.
I agree.
It offers a unique perspective on the history of ideas and the nature of scientific knowledge.
And it's a book that's as relevant today as it was when it was first published.
Almost a century ago.
Yeah.
Well, that brings us to the end of another deep dive.
It does.
We hope you've enjoyed this exploration of the hidden influences behind scientific thought.
Thanks for joining us.
This is Alex and Eve.
Until next time, keep those notes of curiosity flowing.